Okay, quick question. Just, is anyone familiar with software-defined radio? Yeah? Oh, awesome. Have you played with it a lot? Just a little bit? A little bit. Okay, cool.
Just the receiving side.
Okay, fantastic. Has anyone else heard of it? Yeah?
Heard of the concept.
The concept? Okay, cool. I'm not an expert in radio. I'm just going to say that up front. That is the best thing about SDR, right? You don't need to be an expert in radio to do really cool radio hacking things. And over the last decade or so, the cost of the equipment needed to do this kind of work and research has really dropped. Whereas in the past, you were looking at thousands and thousands of pounds. You can get by nowadays with 50, 60 quid to do some really awesome stuff. So some examples of some research that has been done into radio systems before. This is one of my favorite ones. These were some defibrillators. Actually, I think they were more like pacemakers, but either way, medical devices that are implanted into the body. And security researchers were able to recover personal data from these devices, disable them, and in some cases actually induce defibrillation in these medical devices, from across the room. Other things, cars. I mean, it's kind of, I'm sure you guys being slightly younger are probably more used to having all these systems in cars. When I was younger, it was a steering wheel and the wheels, and that's basically it. But nowadays, keyless entry, for example. I don't know if people have seen any videos of people breaking into cars with, by taking advantage of the keyless entry system, where they will have a receiver by the car keys, which is usually just by the person's front door. And then they'll have the transmitter that they can then use to kind of relay the system from the car keys and open the door and drive away. So we'll be looking at those kind of attacks today. Things to do with the tires, they have access to, they have radio devices in there that give the car information about the tire pressure. And again, researchers were able to do things such as take control of the car, being able to start and stop the brakes and affect the speedometer, as we've got an example here. Now this one, I absolutely love. This is something called a Van Eck phreaking, or sometimes known as Tempest. And this is where devices, electronic devices, will emit unintentionally, it's not an intentional thing, but they will emit some kind of RF interference, right? So as data is traveling down these cables, they are kind of emitting data. And by using radios, cheap radios that we have here, we're actually able to kind of capture that data and turn it back into something that we can use. Now, for the longest time, I've only ever seen this done theoretically or in kind of research papers using equipment that I would never have access to. But a few years ago, I was actually playing around with it myself, and it's super easy to do using what I have here as a Hack RF. So maybe it's not super easy to see, but I've got my Hack RF here, and the antenna is quite close to the monitor here. But it's basically picking up the data that's going over the HDMI cable. And then on the laptop, which is not physically connected to the device here in any way, we're able to capture and display the image that's going over that cable, which obviously would allow you to see what someone's doing from across the room. Now, in these test setups, we're only looking at inches. You can only do it from inches away. But in a more, with higher quality equipment, with more money, etc., you could do it from potentially rooms away. In case you're interested in this QR code takes you to a blog post on the DI website. So just very quickly, who am I? Jay, most people call me Jay. I'm a pen tester. I'm interested in things like radio and mobile applications and reverse engineering and things. And these are some Twitter accounts that you can reach out to me. To be honest, I don't really use Twitter much anymore, but I will see a notification if someone messages me. So we're going to talk here about software-defined radio, try to understand what it is. We're going to look at attacking some radio systems and radio devices. We'll be looking at how we can actually go about reverse engineering those systems as well, so identifying those signals and kind of like playing with them. And then at the end, we'll just look at some common wireless protocols that I'm sure you'll be familiar with. So, to start, introduction to SDR, software-defined radio. So, before we talk about SDR, let's just talk about radios, okay? So I'm sure we all know like what a radio is, a radio device, and it kind of looks like this, right? Will be a hardware-based radio. You'll have a few electric components that are kind of chained together. You'll have an antenna, something that kind of captures the signals in the air. They'll go through a few things where it gets the like the frequency will be selected properly. You'll like tune into it potentially especially if you're thinking about a like FM radio receiver. You have the little tuner. This changes like the resonant frequency of the mixer that allows you to tune into the specific signal you want. Eventually it goes to a demodulator, which recovers the actual data from that radio signal. So in the case of an FM radio, that will be like music and voice and things like that. And then it will go to an amplifier and out to a speaker. Now, these things are really cheap to produce. A hardware radio, you could buy these for, pounds, if that, like hardly anything. But the thing about them is they only ever do one thing. You can't use a FM radio receiver to pick up Wi-Fi signals. You can't use a Wi-Fi receiver to do Bluetooth stuff with. They're cheap to create, but they only ever work one way. By the way, if anyone has any questions throughout the talk, feel free to just shout them out. So I'm not an expert with radio, but I'll do my best to answer. Now, that is very different from an SDR, software-defined radio. With an SDR, we basically have the antenna, and it passes that data to basically an ADC or DAC, so analog to digital converter or digital to analog converter, depending on which way we're going. So it takes that data from the air, and it'll be an analog signal, converts it to a digital signal, and then sends that straight to the laptop or computer. And then inside software, we're able to do things like demodulation. So we're able to extract the data from that signal. So what this means is that an SDR, unlike a radio, can almost be any kind of radio. So I could have my LUHack RF here set up to be an FM radio receiver. I could set up to be a Wi-Fi receiver. I can transmit GSM, so like phone calls and things. So we have a lot more flexibility in how we're using these devices. Basically, you can think of SDR as the application of digital signal processing to radio processing. So some examples of some SDRs. I know a couple of people there said that they have used some of probably these cheaper RTL SDR ones, but kind of going up in price, really, you're looking at the USRPs. They are quite expensive. I've actually got a price here up to £1,000, probably beyond that. With USRPs, you actually have like different boards that you can kind of put together to do different things. You're looking at a huge like range of signals that you can like tune into, right? And also you get a lot of data from them. It doesn't really matter too much about that right now, but maybe later on in the talk we'll look at what the difference is between like sample rates and the bandwidth. The two things are tied together. USRP will be full duplex, so you can send and receive data. The LUHack RF is my favorite though. And I say here it's 220 quid. That's the official price. It's actually open source hardware. So if you wanted, you could get the schematics and try and build one yourself, which will also be a lot cheaper. I've also seen them on places like AliExpress, where they were, I think the cheapest one I saw was like 50 quid. I can't say the quality of it. I've not used it. I've only ever used the official hack RFs, but you can get them for like a lot cheaper than this if you don't necessarily want one of the official ones. They are half duplex though, which means they can only send or receive. They can't do both at the same time, which may be limiting depending on what you're trying to achieve. Really good sample rate and bandwidth, and a really good range. I've actually got this range here, so 30 megahertz to 6 gigahertz. I think it's actually higher than that now. I think they've managed to improve the firmware, which has increased that range. Now, what most people might be more familiar with, though, is these ones here, the RTL SDRs. You can get them all different brands and things, but basically they look like this. These are really interesting because they actually are like TV tuners, right? So if you ever wanted to watch TV on your laptop, before kind of like the internet was as it is now, you would have a TV tuner. I used to have a PCI card on my computer. But someone realized that actually what this was doing is it was basically taking the data from the air and passing it to their software and demodulating it and allowing you to watch TV. And they realized that actually by changing that software, they were able to get this to do other things. So these are really awesome because they are so cheap. 15 quid-ish. You can find more expensive ones. They tend to have slightly better hardware. Maybe they will have some more shielding, better antennas, but ultimately they're all the same device. They allow you to capture 2 megahertz of bandwidth at a time. Between this kind of range, and not quite as high as like Wi-Fi, which would be 2.6 gigahertz, but this kind of range. But the big limitation of them is that they only receive, so we can't send data with these. But for a lot of applications, that's actually okay, I think. So we mentioned about the range of what we're able to like listen to with some of these devices. So if we think about the whole radio spectrum, we're kind of looking at like this kind of range. So data sent here. My laptop just blue screened.
Of all the things to cause a display
Yeah.
It's Dell drivers most likely.
Yeah, it could be.
I also have an XPS, and Dell drivers are the worst.
Yeah. It might have impacted the recording though, which is.
That's a bit.
Yeah. I can send you the slides, and then you can add them in manually. And I'll start the recording now again, and then the demos you can put those in.
Yeah, we could do that. We'll figure something out with the recording.
Yeah. Any questions so far? No?
Max, you were sort of saying Wizardry,
How is it able to capture? Well, how is it capable of capture at a frequency higher than its sample rate?
So the sample rate is about the amount of data that it can pick in one go. Where the frequency is not related to the sample rate.
Yeah. So with the like this challenge theorem, you need a sample rate of twice the frequency to sample it.
Yeah, and so that will deal with, so that will be related to the amount of data that you're receiving. So the bandwidth of the signal that you're getting.
Yeah. So. Okay.
Does that make sense? So the frequency that you're able to tune into is separate from the sample rate. Again, I will say that I'm not a radio expert, so that starts to be where it gets a bit beyond my information. But
that sits in front of
yeah.
stuff, the antenna, so you can tune. It helps you tune into where you want to go.
Oh, so are you saying so are you under the assumption that it's getting everything and then you're able to select that in software? Yeah, not quite the same thing. Yeah, as you say, there's you're able to tune the device, which so you're able to move where that section of bandwidth is coming from. as opposed to receiving everything and then using software to tune into it. Let's try again. So yeah, this is obviously a little bit simplified. It's not literally just the DAC in between the antenna and the computer, but yeah, just for this example of for the slide here. So to continue. So it's obviously just a small section of the kind of the available frequencies that we're able to tune into. And is that useful? Now this slide is not meant to actually be read. It's just to show the types of things that are actually used inside this particular spectrum that we can tune into. So you'll have, radio broadcast, TV, for example, is in there. Lots of like small IoT devices will use that. Phones will be included in there as well. So yeah, lots and lots of things that we can tune into. So just as a few examples, obviously like Bluetooth, LTE, so again from mobile phones, Zigbee, GSM, Wi-Fi, all radio technologies that we that use this spectrum. Obviously lots of other consumer electronics as well. Walkie-talkies, baby monitors, these are all things that we're now able to kind of tune into with our SDRs and analyze the data that's going beyond. So wireless keyboards, not so much of a problem anymore because they do apply encryption to the data sent between the keyboard and the device. But yeah, it used to be that it would just be sent in clear text, and then they did apply encryption, but it was always the same encryption. So you could just create a table of mappings of like, oh, if they press an A, then it's going to be this. If it's a B, then it's going to be this. So even though they initially did apply encryption, it wasn't particularly robust. Yeah, as I said, lots of IoT devices as well, just using very simple protocols that we're able to now start to analyze and research with these low-cost SDRs. Now, this one here is my favorite thing. It's called the IME. I've got a video here for, I hope if it plays.
It's IME, the cool way to chat anytime. What's up? Not much here. Just chilling. And your friends can download free trials.
So this was a kid's toy aimed at young girls, where they could type a message on the device, and it would send via radio to the receiver that's plugged into the PC, and then over the internet it would send the message to their friend, to their friend's receiver over USB in the computer, and then off to their device. So the idea is that kids that are playing around in their home, they can make use of their Wi-Fi signal to send messages to their friend. Now, what people realized, this was a toy in America. I don't think it was ever in the UK, but a toy in America. Then it goes kind of offline. The server that is used to send the messages to different people goes offline. The toys are now no longer working. They end up on like eBay and things for hardly any money. And what some people realize is that whilst these devices are not technically SDRs, they do have a software configurable chip. So here's an example of someone changing it to open a garage door, right? So they're able to change the data that this device is sending to send the code to open up the door. I think that's such a great example. So the chips that are in those that do this, they're about like £100 or something. So the fact that they were just in these kids' toys that were being sold for like a few pound on eBay because the system didn't work anymore. Really allowed people to do some really cool stuff. And then spray painting them like different colors and stuff. Now they're quite expensive again. If you can get one, they're like £150 just because people show that you can do some really cool stuff with it. I mentioned baby monitors as well. Now I don't know if this was a baby monitor, but I was at home once playing around with my SDR and I saw a signal and I tuned into it and I could hear one side of a conversation. So I think maybe the neighbor next door potentially had like a baby monitor in the room, maybe they were on the phone and I could hear their side of their phone call because I could tune into their baby monitor. That's what I assume it was, I don't know. So I really like this quote. Apparently it's by Joshua Wright, who did a lot of work into like radio things a while back. I've never heard him say it, but he says, security won't get better until tools for practical exploration of the attack surface are made available. And I definitely agree with that. If anyone kind of remembers Wi-Fi hacking back when Wi-Fi first started to become popular, we didn't have the tools to really do much, even though Wi-Fi was really insecure. I remember actually in one of the first like manuals for a Wi-Fi router that my friend had, that's when we were in high school, it recommended not even adding encryption to the thing. Like that was their official recommendation. And then of course we've got WEP. WEP can be broken in seconds, but we didn't know this until we were able to actually analyze those kind of protocols. Now with SDR, we're actually able to do more general purpose exploration of radio signals. So let's do a quick demo, right? I love doing live demos, absolutely love doing it. They don't always work. So we'll see how it goes. If it doesn't work, I'll either pretend that it did and hope that no one calls me out on it, or I'll try and find some other way to show you. So actually, I'll tell you what, let's use... Let's close this. So I'm going to start with this program called SDR Sharp. It's not a tool I use that often, to be honest, but because I'm using a Windows laptop here, it is one of the better Windows tools for doing this. Later I'll use a VM, I'll show you some of the Linux tools, but let's see if this works. Okay, so this is SDR Sharp. And I'll set the source to be, so these are different SDRs that you can buy, and I'm set it to use the just this one of these devices, and hit play, and yeah. Okay, I think, yeah. So what we're seeing here is I've tuned the device to 104 megahertz, and we can see here, this is the bandwidth that we're able to capture in one go. As I said, these have quite a limited bandwidth that we can look at. The HackRF, we would be able to see significantly more of the spectrum in one go, but this is fine. And what we can see here is some different things. A lot of this is just noise, cosmic background radiation, I guess, like just the kind of static you'll see on a TV, or if you have a radio that's not tuned into a station. But we can see here there is actually a good signal. And so if we try and tune into this, say again?
Sure it's set to FM?
Yeah, it is set to FM, but I need to widen this. And as I said, I don't really use this software that often. There's a way to set the demodulation. It's in the settings. and regardless, you could kind of hear that it's radio, right? FM radio. You can kind of hear the music or voice there. If I could change the... Anyway, we'll look at it again in a bit, but you can kind of see that there's FM radio that we're tuning into and listening to here. So at the moment with this software, we've effectively using the SDR as an FM radio receiver, right? But we can also keep going up, right? And when I was a kid, I was always curious what would happen if you had the FM radio and if you could just keep going past the end of the end of the thing. And this lets us do that. So we can go obviously higher up into the spectrum and find interesting transmissions. Now we are inside a building here, so sometimes it's not always super easy to kind of tune into stuff with a limited antenna as well. But yeah, we're able to kind of go up the spectrum and maybe there will be some interesting things, or even go low as well. I do remember once in London I was playing around with this and I tuned into I think it was like a taxi company. I could hear what they were talking about. I mentioned before tuning into like a neighbour's baby monitor, at least I assume. Another time actually I was playing around with it and I saw a spike and I clicked on it. I didn't hear anything at first, and then I spoke and I heard my own voice coming back through it. I thought that's really weird. And I think what that was the microphone in my laptop transmitting accidentally, just data going through the cables and stuff that the SDR was able to pick up on. So that one was a really, really weird one. So what I have here, if it will work, is a wireless doorbell. And you should see that when I press the button on the doorbell, you can see the data that it's transmitting. Now, of course, that's transmitting probably a series of ones and zeros, and the question will be, can we figure out what those ones and zeros are? Because it's one thing listening to kind of audio transmissions, that like analog transmissions, but I find it more interesting to try and pick up the data from devices. So that's what we're trying to do a bit later. Any questions so far? Yeah?
Was it when you were clicking? No, it's not. Why is it going kind of bumpy?
So the general blockiness is probably just like, it could be, I've got things plugged in here. It's going to be just like general like stuff going on, electronic stuff going on. But yeah, when I press the button, in fact I'd use this one. When I press the button, you'll see on the side here, that is from the doorbell button. All right, so I press it again, go up here. So this screen here, this is what you'll generally see when you're playing around with these kinds of software, is you'll see the FFT, which is this view here, and then here is the waterfall plot. And basically it's just showing, this is showing like the signal over time, I guess. So again, if I press this in the corner here, this is the signal over time. And then this is more of like a live view of the bandwidth.
That's a terrible colour. That's a terrible colour model for the full model.
Yeah, it's probably just the default. As I said, I don't use this software that often. But yeah, you can usually change it. So it's a bit more however you like it. Again, not sure how in this software.
It's just red, and then you have a little bit of blue at the end, and then it goes straight to that.
Yeah. You can probably like change you can usually change it based on what the lower power color is and the higher power color as well. We'll look at that later in some software that I'm a bit more familiar with. But yeah, I wanted to show you just kind of tuning into stuff. So at this point, we're using SDR sharp there as the demodulator, and we're turning the SDR into a rate like an FM radio that we can listen to the radio on. You could change that software to do other things. As some examples, Does anyone remember pages? You just kind of huddling about. A lot of the time, well, they are sent in clear text, those pages, and you can use SDR to tune into those. So if you have the software that will demodulate the paging signals, you can view those messages going through the air. The funny thing is, pages are still being used, right? I will say a friend of mine, because apparently it's illegal to tune into those systems using an SDR. So a friend of mine did that when a couple of years back, and they were able to see messages from like emergency services, messages from like IT systems saying like call this number with the password because the data, the disk is being filled up with whatever. Still lots of like kind of interesting things going along paging systems. So yeah, we can use an SDR, we can tune into that. If we have the software to decode it, then we're able to view that because it's all in clear text.
So what's the sort of range on those then?
It's kind of hard to say exactly. It depends on whether you're just using it by itself, what your antenna's like, whether you've got an amplifier there. I mean, they're okay. Yeah, not great, but okay. Yeah, I mean, you can see we were able to see the signal from a FM radio transmitter from here, okay. They were initially designed to watch TV on, so they kind of were good enough. Another one that I do like is this. So there's a protocol called ADSB, which aircraft, when they're flying, they transmit their location, the longitude, latitude, and speed, and their identifier in clear text. And we're able to use SDRs to tune into that, and there's software that will plot that on a map and show you all the aircraft in your area, which I think is quite interesting. So again, just examples of how we're able to, by changing the software, we're using the hardware to do different things, to tune into different radio protocols. This is an example of the paging systems, POCSAG it's called. So yeah, just some messages that will come up if you're able to find some software to demodulate that. So they're just more like general uses, like tuning into different things. Basically anything going over clear text, we're able to tune into, decode, and view. So if there's anything like secret going across there or interesting, we can tune into that. But let's look at some attacks at some radio systems. The first one is a replay attack. Right, so a replay attack is very simple. Imagine there is somebody, they have a button to like open a garage door or something like that. They press the button, or a car door or something. They press the button, the door opens. As the attacker, we're also going to be receiving this signal, right? If we're in the area, their handheld radio button thing is going to transmit the data to us, and we can also recover that. So then at a later time, we can go back with the captured signal that we have and just replay it back in the air. And of course, the same thing will happen. The door, in this case, will open. Now, the good thing about this is that we actually don't need to understand the signal at all. We just need to know this signal opens the door, turns off the alarm, whatever. So it's very, very, very simple to do a replay attack. There is obviously some security controls in place that stop this happening on some like higher end systems or some more modern systems. They use things like rolling codes, but there are attacks against those as well. So yeah, if you're interested in that kind of thing, read into those rolling codes attack. The basic premise, in one case anyway, is that so with a rolling code, imagine you've got like a clicker to open up a door. The receiver and the remote will have a list of codes that change each time. So you press it, it might send like a 1, press it again, it will send a 4, press it again, it'll send a 6. And the receiver and the transmitter are always in step. So what you can do is if you can jam the original signal, the user is probably going to press the button a couple of times, right? And so you've now actually caught the next like several transmissions, and then while still jamming their signal, you let the first one through. So now you've got the next set of codes that you can go back and use later. That's kind of the easy way to do it. You can also look at ways that you could try and break that rolling code as well. So yeah, replay attacks, data recovery. Now obviously we kind of looked at this a bit before, where we could just like tune into a signal, things like Tempest, which of Van Eck freaking, as I showed you at the beginning, with the recovering the video transmissions through the cable. I also mentioned about how my laptop mic was kind of broadcasting. Oftentimes, yeah, things are transmitting data. There is the assumption that people can't tune into it, but with SDR, we are able to. Denial of service. So if we are sending a kind of stronger signal than other devices in the area, we can stop other devices from working. So I think this one can be quite dangerous actually, because imagine if you're in a situation where like a first responder is trying to find out what's happened in an area, and you're able to jam the walkie-talkies from working and things like that. Yeah, but quite dangerous, especially when used with other attacks, like I mentioned before with the replay attack, and which we might talk about later when we look at some GSM attacks as well. Now this one I think is quite interesting, fuzzing. Is anyone familiar with the concept of fuzzing? Yeah, I think most people. So with fuzzing, it's the idea that you send kind of invalid data to a system to try and cause it to crash. And the reason we might do that is if we can cause it to crash, we might be able to find a security vulnerability. And if we find a security vulnerability, we may be able to exploit that to gain access to the system. So fuzzing is a very powerful tool to do that. Oftentimes, it's mostly done kind of up here in the application level. But with SDR, we're able to actually now start attacking the physical layer. So imagine you've got like a phone with a Wi-Fi chip, and you're trying to find a vulnerability that would allow you to hack into the phone. We might actually fuzz the Wi-Fi chip itself, so the invalid, like not just invalid like Wi-Fi packets, but change what it's kind of seeing when it comes to Wi-Fi, and try to get it to crash, and we can find attacks there. There are people currently doing research into this. They found vulnerabilities in the baseband chips in phones, and even the CPU and the way that it's processing some of that data. Yeah, this is an area that I think really needs a lot more kind of research into it, because it is super powerful, and we're only able to do this with SDR. So we'll try some demos. Let's see again if the last one was pretty successful. But now we'll be using a virtual machine. One of the problems with, I say problems, but one of the things with SDR is it uses a lot of data really quickly, which I'll be able to show you in a bit as well. And because I'm using a VM, we'll see how it works. So we are going to look at the hack RF in this case. So this, God. Okay, this is a tool called GNU Radio Companion, right? And this lets us create software for our software-defined radio by using this kind of like drag and drop interface. So let's try and just do something quite simple, right? I'll try and create some software that will tune into the wireless doorbell that we've got here and see if we can see the data. So actually, yeah, we can look at, this is what I made earlier. Let's have a look. Okay, so these ones that are lighter colored are enabled, these ones are disabled. We just leave those disabled for now. But you can see with these, basically these two blocks here, this Osmocom source, which is the SDR, that's a block representing the SDR, and then the Qt GUI frequency sync, right? We're joining those together, and that's basically taking the data from the SDR and placing it into this output here, which is a GUI element. And assuming the SDR is being picked up correctly. Yeah, it allows us to kind of visualize that data. So we're taking the data from the SDR, place it into a GUI element, and then if we press that, we're able to see the data going across, right? Now this is obviously very similar to what we saw before. Not as nice, admittedly, but very similar. We have the graph here. I've got a little element here that allows me to kind of tune it, and that's basically it. Now, what we can do more than we saw before is rather than only using the GUI sync, we can actually use a file sync as well. All right, so if I enable this one, so as well as going out to the user interface, it's also going to be that same data is going to go into a file I'm going to call doorbell3. Okay. So again, ignore these grayed out ones. It's just these colored ones here. This is for the tuning element I added in. But so the data is going to come in from the SDR, be output into the UI so we can see it, and also be output into a file. Okay, so if we run this, press the button, stop that. We've now stored that data from the air into a file. And let me just I just ran that for like a second or so, a couple of seconds, and that file is 33 megabytes. I've got the sample rate set as I think that's 1 million samples a second, right? The HackRF supports up to 20. So I've really narrowed down the amount of data we're actually capturing in one time, because if I put it onto the full 20, the file is going to be like hundreds and hundreds of megabytes in like seconds. So it's always best to reduce the sample rate as much as possible. If you reduce it too much, you're not going to get enough data though, so it's kind of getting that balance. In fact, let's bump it up a bit just to kind of, just in case you're curious. I think 20 is the maximum. I'll change that into doorbell 4 though. The VM may break. Let's see, hope not. So I won't press the doorbell, but I run it. I'll stop it. Yeah, 120 megs for just that little bit of time running. So it gets really big really quickly. Okay, so if you want to do a replay attack, what do you think the next step might be? Who can guess?
Broadcast it out on the radio.
Exactly. So we've saved the data into a file. So now if we, instead of using the Osmocom source, we'll have a file source. And instead of having a file sync, we'll have the Osmocom sync. All right, so we are going to we'll put it back into the GUI as well, so we can see it. And also, I will just change the frequency to the same frequency we stored it as. So basically, with GNU Radio Companion, I've got this GUI range element in the UI that I've called Freq, F-R-E-Q, and I've set that up to be the frequency of the doorbell. And so in the Osmocom sync here, I'm just telling it to use that frequency to kind of output. Now, that's doorbell 3, that wasn't it? So this is the file that we saved it into. Now, if you do these kind of attacks, well, you know, if you're using this in research and things, you do need to be careful, because the HackRF in this case has picked up everything within that 1 megahertz range that is being broadcast, just for that second, but it's catching everything. Now, in theory, if within that signal somebody had transmitted something to, you know, maybe increased, you know, their pacemaker data or something, we would also be sending that back out into the air. So ideally what you would want to do is do some filtering and things before you actually just send kind of like data you've captured back into the air. Now, I'm going to hope that we've not captured anything kind of dangerous, because I don't have time to set up a filter. And let's hope this works. Sometimes it can be a little bit temperamental, and sometimes it works first time. Yeah, okay. So without pressing the doorbell now, we've able to get the doorbell to ring. So again, you know, this case it is just a doorbell, but you know, this could be kind of any IoT device that we're kind of interested in kind of analyzing. Does that make sense to everyone? Yeah? No questions? Okay.
Actually, you said IoT device. Would this also apply to device? How often does this also apply to devices using the internet protocol?
Well, like Zigbee and things like that, or
yeah, sort of.
Yeah. So yeah, I mean these are going to be more like low-powered, low-cost devices. I mean, I think, you know, things like doorbells and stuff. As it becomes easier to do these kinds of attacks, companies have started to build like more complex protocols. So something like a simple replay attack is probably not going to work on a Hue light bulb or something like that. So yeah, in those cases you're going to need to attack the protocol specifically, and there are tools and techniques for that, which we'll talk a little bit at the end, more in relation to Bluetooth, but yeah. So yeah, these like replay attacks, specifically this replay attack, you know, probably won't work with a more defined protocol. But if it's something like a device like this, then yeah. Also, like in the case of Bluetooth, some versions don't apply encryption anyway, so it's still useful to be able to view that, to be able to capture and view that data. Sometimes it doesn't use encryption on the physical layer, but the application itself is using encryption. So it's kind of hard to say on like a specific like general case. Okay, the demo worked. I'm happy about that. Okay, so identifying signals. Obviously, it's one thing to be able to just like capture a signal, but usually we want to understand what data is actually being sent. So, you know, in this case, there is the doorbell, and it is going to send some kind of like, you know, message to the, you know, the controller is going to send some button to the receiver here. But what if you wanted to make another doorbell ring, or a doorbell where we're not able to capture the data. Or what if it wasn't a doorbell? What if it was like a lock or something like that? So it can often be useful to like analyze the data rather than just capturing it. There's kind of there's three, but we'll talk about two of them. Two main ways that these devices send signals. One is called on-off keying, where it's a change in amplitude, i.e. loudness of the signal, is what encodes the ones and zeros, right? So you'll have a device, it will send a signal and it'll send like a loud signal, quiet signal, loud signal, quiet signal, and that will be like a 1 0 1 0. That's called on-off keying. Yeah, pretty straightforward. That is kind of like the simplest way. Most low-cost devices will use probably OOK, on-off keying. Right? Does that make sense? It's just like send, don't send, send, don't send, send, don't send, and it's just like ones and zeros going through the air that way. And what that tends to look like is this. You can kind of see with these graphs, you can see basically the ones and zeros going over the air, right? And at that point, you're using skills that people may be more familiar with when it comes to reverse engineering. Now, in this talk, we're not really going down that route. We're just looking at capturing this data and analyzing it. But there's lots of information on how to like reverse binary protocols, and that's probably what you'll now start to look at. So you can see you can kind of quite easily move into a more familiar domain rather than radio, which, as I've admitted a few times, is not my expertise. This is the kind of thing I'm more interested in. Once it becomes ones and zeros, then I'm happy. Now, the other approach that you might see is called frequency shift keying. So that is where a device will send ones and zeros by changing between two different frequencies. So one frequency would be a 1, another one will be a 0. And what that will usually look like is this, and you kind of see it moving backwards and forwards between the two frequencies. So 1 0 1 0, etc. So let's try and take a look at that with the doorbell and see what it's doing. So I've captured this signal, doorbell 3. We'll take a look at it. This is a tool that I like called Inspectrum. We'll look at doorbell 3. So many errors. Okay. Now, I've purposely not mentioned this line that's going through it. It's an artifact, really, from the way that the devices capture data. It's called the DC offset. Again, not really my expertise, something to do with the maths of how it's capturing data. But you can you can ignore it. It's just a weird artifact. In a lot of the software as well, there is actually a button to kind of remove that, but you can kind of ignore it for now. So this is Inspectrum, and you can kind of see when I press the doorbell, this is what's being sent over the air. Now, we want to get these into the ones and zeros, right? So we can see what's actually being sent. You could sit there with a pen and paper and try to figure it out. That's doable, kind of messy. What I like to do, and one of the reasons why I like Inspectrum, is because we can use this feature here. We could use that feature there. Okay, let's try again. Yeah. Okay. Oh. Right, hold on. I'm going to bring this back into my other screen and see if I can get working here. know, something about probably just something to do with the screens or whatever. Yeah. So one good thing about in Spectrum is now by changing some of these values here, you can kind of make the signal a bit easier or harder to see. So I tend to try and get it to the point where it's kind of like a nice line like that. And then using this cursor feature, you can kind of highlight the data that's being sent. And sometimes it gets a bit funky, and then you just kind of like try and get it to fit properly. Move it up a bit. Something like that, I guess. Yeah, 1 0 1 1 blah 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 blah. Yeah, that looks about right to me. And then we can actually use in Spectrum and ask it to tell us like what the ones and zeros are there. So we can add no, not that. And threshold. This up a bit. And so now, if you right-click on this and say, extract symbols to stand it out, and we go back to the terminal, you see it's giving us the ones and zeros. So we can see quite easily the binary that's being sent through the air. Now from here, the question is like, what do you do with that? Again, that's where you start to look at more common reverse engineering techniques. Yeah. Now, this was actually like how I used to do things, because this was the easiest way. And actually, before in Spectrum, it was even harder. In Spectrum made it so much easier just to get this string of ones and zeros. But over the last couple of years, I've been using this tool called Universal Radio Hacker, which I find to be really, really cool. So it has a few different modes here: Spectrum Analyzer, Record Signal, and Sniff Protocol. So this is more of like my current approach to this. So let's look at the Hack RF. The frequency, yeah, I kind of know roughly what that is because of using like SDR Sharp or GQRX is another similar tool that is in Linux. Let's stick the gain up a bit, and let's start. And then you'll see, again, we can see kind of where the signal is here. If you kind of click on this, it saves that frequency there. So you found the signal, you click on it, then you can go to record signal, right? It's kept the same data. You can hit start. Now, one thing about a Universal Radio Hacker is sometimes it can be a little bit inconsistent, I guess, or a little bit finicky. So I like to use in Spectrum to actually look at the data myself rather than just trusting Universal Radio Hacker. But when it does work, it works really well. So if we start, record, stop, it's now saved that data. We can save it. Just give it the default name. And now it will analyze it. Yeah, I mean, I can see that this hasn't really worked, but let's try auto detect parameters, see what that does. Yeah, as I said, sometimes it's a bit flaky. But I did capture another one the other day. Let's see which one was it? Let's try this one. Yeah, so this one down, get rid of this one. So yeah, that's why sometimes using in Spectrum, you can kind of see it, and then you can use URH to kind of analyze it. And when it works and when it matches what you're expecting, then it works really well. So in this case, this was a signal that I captured. And you can see the ones and zeros that are going through the air. Now, something that's interesting to see is it's mostly the same data, right? So if we go back to it in Spectrum, did I close it? I think I did. But let's go back to in Spectrum. Open doorbell 3. So I keep dragging the mouse outside the VM. You'll see that it looks like it's sending whatever. It looks like it's sending like a chunk of data, then a gap, then a chunk of data, and then it's a gap and a chunk of data. It does that loads of times. And when we look into Universal Radio Hacker, we can see the same thing, right? It sends just this same string over and over again. Now, I reckon the reason why it's doing that is because these devices are kind of low cost. Rather than having some like complex, acknowledgement protocol or something like that, some like handshake, it's just sends the data over and over again and hopes at least one of them will go through. So I think that's kind of what it's doing. And so from here, yeah, we have these ones and zeros, and if we want, we can set it to show us as right, let's try, I'll put it back on here and see if I can change it. So I set that to be displayed as hex instead, so we can see the actual hex bytes that are going through. I do actually have 2 doorbells here, so you could compare them and see what the difference is between them. And again, I won't do it now, just in saving time. But what you'll see is there will be like a byte that's different. So one doorbell sends one value. The other one sends a very similar value, but with just a few bits different. What that would mean, though, is if there was a third one, if my neighbor was using this and I wasn't able to capture their signal, I could maybe just try and brute force their code and try and get their doorbell to ring. With UHR as well, one cool thing that you can do is you can actually just replay that signal that you captured. So it's very easy to then just change some of these bytes. So if I change this one to C9, for example, and then play it, and then it will send that instead. So really powerful tool. And again, like when I was starting to use SDRs, this didn't exist, but this has really changed like the speed at which you can analyze some of these signals. I won't demonstrate it, but because I don't think there's any need anymore. Since using this, I've not really had the need to do it. But before, I used to use this thing called the Yardstick 1. Now, you remember the IME toy that I showed at the beginning? This has basically the same chip in it. So what this allows you to do is you can basically give it some data and say transmit it on this frequency with this modulation. So you say, FSK on this frequency and this data. So what I would normally do is using Spectrum to see the data, export the bits, and then I could feed that into the Yardstick 1. But yeah, given the fact that Universal Radio Hacker is so good now, I rarely use the Yardstick 1, to be honest. So there's no real point in showing it. Okay, so just quickly, some common like radio protocols, some attacks I know on them. It's a little bit of the older stuff just because the newer protocols tend to have more security built in, but GSM, obviously, this is like mobile phones. an older mobile phone protocol, 2G, I think it was. You have the handset, you have the base station. The base station basically tells the handset whether the communication should be encrypted or not. If the encryption is disabled, in some countries it wasn't legal to enable encryption, then you can use the SDR to just tune into that and recover that data.
Are you talking about Russia?
So I think India was the example that I saw. I'm not sure about Russia. I think in America they might have had it disabled as well, like back when it was kind of like a new technology. But I'm not sure about Russia. Be interesting to find out though. But another attack that you can do is, as I said, the base station basically sets the encryption. If you set up your HackRF to act as the base station, if your power is stronger than the actual base station, the mobile will connect to your HackRF or your SDR, and then you can just tell it to not enable encryption. So you perform like a man-in-the-middle attack there. When encryption is enabled, you can also capture that data and crack it. It's actually really easy to crack. You need some rainbow tables. Those rainbow tables are, how big are they? I think like 1.5 terabytes or something, so huge. But with those rainbow tables, you can decrypt GSM traffic when it's in use. It's not in use that often. One thing that used to happen, I'm not sure if this is still the case, I think it might be, but mobile phones will often connect to the strongest base station around, regardless of what technology it supports. So one attack that used to happen is that you would, even if the phone was using 4G or something, or 5G, you can get it to use GSM by just providing a really strong GSM base station. And this is something that like the police used to do. They'd have a tool called a Stingray that would do that. You go into an area, all the mobile phones would connect to them, and they would be able to intercept communications. Despite your phone supporting 4G, this would like force it to downgrade. So yeah, replay attacks, sniffing, denial of service, fuzzing, and crypto attacks, because the crypto for GSM is very weak. Bluetooth, some details about how it does channel hopping, but the important part is the encryption when it is used. This is so Bluetooth Low Energy specifically. The encryption key, the LTK, is created from either a pin or a default value. The default value, I think, is just basically the pin, but all zeros, or the pin is just like a 6-digit pin. With some of these types of equipment, you can capture the Bluetooth message at the end and brute force the temporal key to get the short-term key to get the long-term key. If the key is transmitted out of bands, such as NFC, then you can't perform this kind of attack. But this is one way that we'd use to attack Bluetooth. Another way that I kind of like doing was using the HackRF to be a Bluetooth device. And there was this one pen test I was on where the goal was to unlock a tablet, and the tablet should only be unlocked when somebody with a Bluetooth, like they had like a Bluetooth badge or something on their belt, and the idea was that they go up to the tablet and then it unlocks, and when they go away it automatically locks. I was able to use the HackRF to basically generate that exact same Bluetooth packet and get the device to unlock. So yeah, if you are interested in some of the work that I've done on Bluetooth, QR code here. But as you can see, 2015, so a little bit outdated. There are some specialist tools for doing Bluetooth work. The Ubertooth. Honestly, I find they're not super useful anymore, but they can be in some situations. Zigbee has problems with the key exchange. So when you add a new Zigbee device onto a network, that device gets the key, and we can use the SDR to try and tune into that and capture the key. Poor key exchange, I'd say. of course, fuzzing, denial of service we can perform as well. So that's the end of the talk, basically. I just find it kind of interesting to see, you know, radio devices. To do this kind of work, you needed a load of different stuff, whereas nowadays you just need kind of like a hack RF. That's basically all you need. Yeah, that's the end of the talk.